Hi, everybody. Great to see you all. Hello, and welcome to the Live More Life, the Good News About Your Health podcast. The podcast where we dive deep into the world of healthcare, longevity, and health and wellness to bring you the most up-to-date insights and recent breakthroughs in improving your personal health. I'm Dr. Eric Reese. I'm your host and healthcare co-pilot on this journey to a healthier, happier you. And every week, we're going to explore exciting topics ranging from diet, exercise, nutrition, mindsets, peptides, personalized medicine, all while discussing the most recent medical breakthroughs and technologies that are trending on the market today. We'll be combining the integration of both Western and holistic medicine practices into one exciting perspective, all designed to empower you with the knowledge and motivation to live your best life. And today's episode is going to be one for the record books. We're going to be talking with a dear colleague of mine, the brilliant Dr. Rupert Holms, who's a renowned researcher. He's a renowned biochemist. He's an entrepreneur. I mean, this man has a rapport that is second to none. And Rupert has some pretty interesting things to discuss about today. Our overall general focus is going to be on personalized medicine, but as with most of these discussions and conversations, there's always a hint about longevity, quality of life, and what things we can do today to help support ourselves living into tomorrow. And so I am beyond grateful to have Rupert joining us. And here is the man, the myth, the legend himself. Rupert, thank you so much for joining us on this episode of the Live More Life podcast.
Eric, thank you very much for that introduction. Very generous towards my development. But anyway,
I have a lot of appreciation for you. And Rupert, I know I didn't even do your background report justice. I know there's so many things you have done. So I think for those who are joining us, it would be great for you to give a little bit more background about kind of where you started, where you came from, and kind of what brought you to where you are today.
Okay, so my academic background is I'm a Ph.D. in molecular biology from University of Edinburgh. But I've got a rather unusual career because when I finished my PhD, I was actually working that time in site-directed mutagenesis. Well, this is right at the beginning of it. I'm now getting cited as one of the founders of that type of technology. But I actually jumped out of academia and became a life science investment manager. So for 5 years, I was on the sort of investment side of technology in the health area and the life science area. And actually early on in that period, that's in the 80s I'm talking about now, I've got to explain, I'm 66, I've got my hair still, it's the right color.
You're doing something right.
So the drugs work. I've also got 10 kids. I've got an age span between like 38 as the oldest to 18 months as the youngest. So anyway, life is good for living and, attitude plus good pharmaceuticals, good combination. Okay. So basically I have a technical background, but I've also got a financial background. And in the 80s, the HIV epidemic hit in 1984. And actually for the first year of general panic, I was actually out funding the UK government because I was sitting in a Swiss bank and said, we've got to do something about this. And so I actually raised a $50 million fund. And we started to invest in companies that already existed, but also putting profits into startups which had unusual technologies. And later on, I'll be talking about the technology of Ezrin peptides, which actually stretched right back to that time because we were working on HIV peptide vaccine approaches. And we found a bit of the co-protein of HIV that mimics a human protein. And at that time, no one knew what this was all about. Anyway, the mimicked protein was called Ezrin. And it turned out this was a sort of road of exploration that sort of started in like 93 and went via Russia because I actually ended up building a pharmaceutical business in Moscow. And then now, because of all the international tensions, I'm back in the UK. I had to leave Moscow. Literally, I left Moscow January 22. War starts in February. That's a tight timing.
Good timing.
Yeah. So now I'm back here in London, and I've got Regent's Park over there. We've got London Zoo. You can hear the lions roar in the morning, and you seriously can. And so I'm doing science here in the UK, collaborating with friends and colleagues in the US and all over Europe, and actually making peptides in China. So I operate quite globally.
Love that.
That's introduction.
You are an international mystery man at that point. I mean, I think there's so many awesome things to pull out from that. And I think that there's something to be said about those who start off in academia or have at least a time in academia. They get into industry. And for you, I mean, to even develop and create your own company is so remarkable and so inspiring to so many who maybe want to take that similar path. Rupert, I'm curious, in the early days when you were working on HIV and AIDS and you were working in the lab, what were some of the thinkings and the progressive ways of, moving forward that you were a part of and that you started to notice that kind of took you down the path of creating and really finding out Ezrin and how it was benefiting us from an inflammatory and from an immune standpoint?
Right. Yeah, I mean, right at the beginning, there was actually quite a lot of controversy in the 80s about really what AIDS was, because even though it became clear there was a virus involved, right at the beginning, people really didn't know. They thought it might be a lifestyle question. It might have been use of certain type of drugs. They really didn't know. But then actually it was Luc Montagnier who discovered the virus. And when I got into it, I thought there's no point going down the traditional route of trying to make a vaccine because, you're basically working on something that's damaging the immune system, and therefore vaccines probably aren't going to work that well. So we went for non-conventional approaches. And the way I put this together was, at this point, I'm not an academic, I'm sitting in a bank, but I put together research teams from MRC, Medical Research Council in this country, University College London in London, obviously, but also teams in the US and San Antonio, Texas, very good team at the Southwest Foundation. And we got the funding together partly through the funds I had already organized, but also we did a license deal with Becton Dickinson. They put up 2 million. Because in fact, one of the projects was an antibody project. Becton Dickinson happened to own the antibody. So I'm opportunistic, in the sense that I look for, you encounter problems, you look for solutions. And I think laterally, so, I do things in a slightly different way than, say, the mainstream will go down one narrow path and throw a lot of money at it, but may not necessarily be the way forward, So.
I feel like that's kind of a similar spot of where we are currently at today with looking at longevity and whether it's biohacking or even personalized medicine, because most people kind of are down this path of, okay, well, you can do so many cold plunges and so many sauna sessions and you can, do so much to support NAD+, but at the end of the day, there's so many other mechanisms at play. And this is one of the reasons why we started the Live More Life podcast, is because I know that there are people out there like you who have boots on the ground, who have so much knowledge and experience, but you may not be on the cover of, New York Times or the Herald or in these major publications because, they just may not know as much about what you're doing. So, for those who are interested in keeping a space, the reason we start the podcast is to educate them, but then more importantly to continue to follow up and support. So if there's anybody on this podcast who really wants to learn more about this and get more in contact with individuals we come into contact with, then go to nobodystudios.com/newsletter. We are creating a newsletter specifically focused on this space. And Rupert, for you to kind of elaborate a bit more, what are some current trends today in personalized medicine that you think have merit? What are some personalized trends in medicine today that you think are going down the wrong path?
Okay. I'll first go the wrong path.
Yeah, sure. Probably easier that way.
I think, people still got very simplistic ideas about how living systems work.
Yeah.
And, there won't be a single target solution. It's not suddenly you're going to suppress something or activate something, and then you're suddenly going to be healthy for the rest of your life. Sure. Generally, living systems are highly complex interacting systems, and you've got to sort of bias them towards positive directions. But you can't have a sort of aggressive drug approach. You've got to, have multiple strategies. And some people, because of genetic variation, some strategies will work better than others. Specifically, I'll talk to you a bit later about this, but the anti-inflammation area is looking very, very interesting because that isn't a sort of health issue over a long period of time. The less inflammation you have, the better your general health is. You can approach that, from a diet point of view, but there are specific immunological ways you can approach that. the big breakthrough over 30, 40 years ago was the understanding that you can change things. For a long time, people had this idea that, your body is a bit like a car that's wearing out and getting rusty and bits fall off, and eventually it just doesn't work anymore. But in fact, really, the living systems are all programmed to have a certain lifespan. And there's a sort of general understanding that, you can get a big variation between, related species. I mean, for example, songbirds, you can get some songbirds that live 2 or 3 years. You can get some parrots that live 120 years. Now, they're fundamentally very, very similar. But for some reason, some ecological adaptation has meant that little songbird that doesn't live very long, it was a more efficient solution for the whole species. They fly around quickly, they grab as many insects as possible, have as many babies as possible, and it's all over. But I'm saying that's not the ultimate destiny. There are lots of possibilities to change some of that. I mean, I think we're still far, far away from getting any progress on absolute immortality.
Sure.
But longevity is doable. We can change life expectancy. We can change health span, definitely.
Yeah. My understanding with where a lot of this research is going is that people are really looking at immune function or the lack thereof, immune dysfunction. They're also really keen on focusing on mitochondrial function, which, when you think of back in even the 80s or 90s, we look at mitochondria. It's like, okay, these are the powerhouses of the cell. They produce ATP. But now we know a lot more, right? So they have immune functioning properties or immune regulating properties. They also have inflammatory regulating properties, and that's for better or for worse. There's discussions about cells and what the difference is between old cells versus new cells, and how these senescent cells kind of stick around and just kind of clog up the pipes, for the lack of a better term. And so with your understanding and kind of what you've done with Ezrin, and I know that you are currently working on the next generation of what Ezrin looks like, I think it would be probably a good time to just talk about the evolution of the thinking behind that and where things are moving and what do these molecules actually do?
Okay. Well, thank you. Okay, I'll go back to the beginning. Well, not right back to the beginning, but the Ezrin peptide project came out as HIV vaccine work. When we realized that HIV is mimicking this structure in human Ezrin, we understood that there is, whenever you see a virus retaining a certain structure, even though it's mutating very quickly, it's because it has functional importance. And so early on, we thought, okay, maybe we're dealing with some sort of allergy cross-reactivity. Here you've got a virus with a bit of human on it. Maybe your body sees that as foreign, sees the structure and the human being as foreign as well, and you start to get autoreactivity. So, in fact, at that time, it's the early 90s, a lot of HIV positive people had not much hope. The doctors were saying, sorry, we don't have the drugs for you. 6 months, we've probably only got 6 months. So I had volunteers coming to me at that time. And the first volunteer, I actually said, look, legally, I can't really, prescribe a peptide to you. It's totally experimental. But if you want to do it, I can tell you where to get it made and, go to your consultant GP, or consultant at the hospital and see if they'll monitor you. This HIV guy was really organized and he did all of that. And in the end, we did a study at Ealing Hospital, just a one-person anecdotal study. His viral load went down, CD4s went up, CD8s went down. Basically, he was going the right direction of health. And then on and off, I had some contact with him for about 10 years. And basically, he did not, even though he had basically been given a death sentence by his doctor when he met me, he was powering away. I mean, last contact I was like 2002, but I'm saying for a 10-year period, he was definitely, relatively healthy. I mean, he was one of these mavericks who tries everything new. So
Sure.
he was trying all sorts of protease inhibitors and combinations. And, so I can't say, we totally changed his life at that point, but we definitely gave him the extra time then to investigate other possibilities.
That's interesting.
That's the origin of the project anyway. So.
Yeah. Rupert, I think it might make sense to kind of discuss a bit more about like what is a peptide? People are hearing about BPC 157. They're hearing about different molecules out in the market. And I think there's just a massive lack of understanding overall about what these compounds are, they actually do. Can you explain that a bit?
Sure. Okay. First, a peptide is a string of amino acids. It's a polymer. Okay. So you have 21 amino acids. They are relatively simple molecules. They've got an amino on one end and they've got an acid on the other end. That's why they're called amino acids. And they have a side chain. That's basically what an amino acid is. And you stick them all together and they tend to spontaneously form shapes. So you get the two standard shapes are called the alpha helix, which looks a bit like a DNA helix, but it's a single helix. And you get this thing called a beta pleated sheet where you get anti-parallel strands that line up with each other. Generally, the therapeutic peptides tend to form alpha helices. And for example, in your body, there are things like melanocyte stimulating hormone or even oxytocin, which are peptide based. And they're quite short peptides, 10 to 15 amino acids. The Ezrin peptide is a 14 amino acid peptide. The reason we originally chose to work at that size range was because in immunity, you have what's called an antigen presentation system. And it literally like a protein that shows protein signals in the form of peptides, okay? And the standard size there is between 8 and 14 amino acids. So it means this is like a language. It's like a word for the living system to recognize that bit of information. And generally, there are very specific signals that are delivered by these sort of peptide words. And they can be as short as 4 amino acids. When they get bigger, when they get 20 or 30 amino acids, they start to really fold up into what's called the tertiary structure. That's when you get the big sort of blobby shape of a protein. Okay. But when you have the shorter peptides, they have what's called the secondary structure, which is this much more rigid shape. But what they're actually doing is communicating with other proteins. And this is another thing to understand is that, okay, we tend to think, when the basics of biology 101 is that you have DNA, RNA, protein, and somehow RNA and DNA are sort of driving the whole system. It doesn't work that way. It's very, very likely that the beginning of life was a protein-based system. And a lot of the original functions, which would be very simple, would be protein interactions. But the way the DNA and RNA came along is a bit like your external hard drive on a computer. So you sort of imagine a bunch of proteins together. That's your CPU, your central processing unit. That's what gets stuff done, metabolism. They can grow, but they can't really store their information. But there's a certain amount of copying going on. It's possible between proteins. So all of these other things like DNA and RNA came later. So sorry, I'm giving you a big detour there, but
yeah, it's all good.
But that is origin of life stuff. I mean, I must also draw your attention. New big discovery. They found a protein in a meteorite. All right, it hasn't been fully published yet. It's on one of these sort of pre-publication sites, but it's like a 16 amino acid triple glycine-like protein. Now, if you start to find proteins in meteorites, they've already found amino acids, then probably the basic material that became life was developed from an extraterrestrial sources. Okay.
Interesting.
That's cool.
Interesting. Very interesting. Yeah. And so when you take a look at, just you working within this peptide kind of space, how do peptides actually exert an anti-inflammatory response, or we'll say a healing response in some way, shape, or form? Because maybe that isn't the exact mechanism. Tell us a little bit about that functionality.
Okay. In principle, peptides will bind to a receptor on a cell surface and deliver a specific signal. And they can generally interact with other proteins to make the proteins change shape. And we tend to think of in pharmaceuticals like small molecules, some big receptor, and it's like a very simple switch. But in reality, proteins, many, many different types of proteins are clustered on the cell surface, on the undersurface of the cell membrane. And it's sort of big, concerted sort of waves of blobbiness that are happening all the time, and these are charge interactions, so it's negative charges, positive charges, some what are called hydrogen bonding forces. So I'm saying it's very complicated. It's sort of like touchy-feely sort of interaction, which is then what tells the cells what to do. And the more we've learned about how this works, I mean, for example, when you have an organ developing, what controls organ size is cells can actually feel what's the amount of pressure on the outside of the cell. And there's a specific signaling pathway inside the cell, which switches on and off protein synthesis, genes. It's called the hippo pathway. It was originally found in flies. But what I'm saying is that the big thrust at the moment in biology is what's called systems biology. It's trying to understand how everything works in one big process rather than pointing at some specific thing. Okay. So basically, back to the question, how do you switch off inflammation? Well, a lot of these cell surface protein structures will be inducing signals into the cell. And by shape changing these surface structures, you can switch on and off function. I mean, it's the simplest way to say what's going on.
Like lock and key mechanism, right?
Yeah, but it's much more complicated than a simple lock and simple key. You should imagine a door with multiple locks on it that are made of jelly, and then you're somewhere near the truth.
A little bit more, elusive, as you would allude to, yeah?
Yeah.
Interesting. So tell me a bit more about the Ezrin peptide. And I know you're working on a newer molecule that might actually have a more of an effective delivery mechanism. Tell us a little bit more about those.
Okay. So Ezrin peptides themselves, as I say, they came out of this HIV program. I did most of the development work in Russia. That was just an accident. Life is always an accident. What happened was in the mid-90s, actually Russia was a very fashionable place to invest. And I'd already started a small business inside what's called the Gamaleya Institute in northwest Moscow. And so sort of immunology, microbiology specialist institute. And I just happened to be able to get the funding for the Russian business plus the Ezrin peptide project. And so I just shipped the whole thing off to Russia. And I was in Russia half the time for the next 30 years. So what we did there was really, and actually Russian immunologists are really good. And we sort of worked out what really is going on. We found it's something quite complicated. That is that final result by year 2000, we understood we were down-regulating inflammation, but up-regulating programmed immunity with the same molecule. So what we were obviously interacting with is some really important central control mechanism. Okay. And then later we found that we were also encouraging wound healing. We did some clinical experiments even on radiation damage. I mean, this is not bombs. This is, when they do tumor radiotherapy, quite often you get skin damage if you send these sort of ionized radiation through your skin to get at the tumor. And so they were looking at surface damage and found Ezrin peptides work there. But what we now know about them is that they have this combination of characteristics, which is, protecting you by developing your effective immunity, that is the T and B cell immunity, that's called adaptive immunity, but down-regulating inflammation. So, for example, we did about 25 clinical trials in different disease areas. We start off in HIV and opportunistic infection, and that's quite complicated because you've got a patient who's got lots of different infections. So we then focused on things like human papillomavirus. We looked at herpes viruses. We looked at chlamydia, even some of the protozoan sexual infections like that. And so in each infection, we could, and generally we were dealing with the patients who had drug-resistant infections, chronic infections, and using this strategy, we could stop those infections. So we have patients who've been coming back to the clinic all the time because they can't get rid of the infection, the antibiotics don't work, or antivirals don't work, but we could solve the problem. And that's back, work I was doing sort of late 90s up to like 2010, something like that. We then went into respiratory diseases, and particularly we started looking at inflammatory respiratory diseases, a sort of pneumonia-like problem. And then along comes COVID. And so, in fact, for me, most people go, "Oh my God, I got COVID." I go, "Wow, experimental opportunity." So I knew I got, SARS-CoV.
A proper research scientist.
Yeah, so I'm whacking up my own drugs, and I fixed it. I literally fixed the problem in 5 days. So I had no COVID. But then I thought, this is interesting because, okay, what I'm actually doing is amplifying my antiviral immunity. So the next question is, how long am I going to be protected by what I've just done? And so I never took the COVID vaccines, none of them. But I was traveling still quite a lot. So I was getting PCR tests all the time, and I never got SARS-CoV-2 ever again. Right? So what I had done is upregulated my natural immunity. Now, more recently, I'm looking at sort of age-related medicine because some of the work we've done in the last 2 years is a lot of people have come to me with long COVID, and actually a lot of people who say they've got long COVID have actually got like a mRNA vaccine injury, and a lot of people got inflammatory reactions to these vaccines. And generally, when people are, we've had about 100 volunteers, okay? I can't call it a clinical trial because each patient's different. We're not controlling it. We're not actually allowed to do it other than unmet medical need.
An N of 1, yep.
Yeah. But the result has been about half the patients get symptom relief or significant benefit, and actually 10% of the patients, we seem to be curing them, okay? But what was really interesting is some of these patients also have comorbidities. And so, for example, some patients would be complaining about myocarditis, pain in their chest mainly after vaccines, and said, wow, it just disappeared. And we had other patients who had ankylosing spondylitis, which is a back disease, inflammatory back disease. Again, on treatment, it stopped. And then we thought, okay, maybe this is just an anti-inflammation effect. We haven't done anything beyond that. But we did a follow-up 9 months later and said, it's still gone, right? So this guy had this back problem for 12 years. He got COVID. He then got long COVID. He then came to me. We treated his long COVID, which we basically knocked out his brain fog problem. But at the same time, we knocked out his, back inflammation problem as well.
Interesting.
And it was a permanent, I can't say permanent, but it was a persistent fix for his problem. So anyway, that's serendipity, medicine, and science. You do stuff, it works.
It's lovely. It's I think it just comes back to the point of being in clinical practice has just reminded me too about people are allowed to have more than one thing going on, but you can't separate to the psychology versus the structural versus the immune versus the neurological. Everything is going to affect itself in some way, shape, or form. Everything has trade-offs, right? And you mentioned this early on as well too about how when you affect one mechanism, and inevitably there are going to be other mechanisms that are affected along the way. That's just how the human brain and body and our metabolism works, right? This is all lovely biochemistry and different mechanisms. And so getting too much caught up in the trees and not being able to see the forest is something that we see quite often. Unfortunately, I feel as though, especially in the longevity and the personalized medicine space. So Rupert, with that being said, tell us about, I know you have your Rep G3 molecule that you're working on and moving forward with, and we're kind of getting close to our time here on this as well. Okay. So tell us about what you're working on today, what is exciting for you, and why you're waking up in the morning with this vigor, and you being, the age that you are and still having a full head of hair and being a parent and still having this vitality. I mean, I think most people on this that are viewing this would say that they're a bit envious of what you've got going on. So tell us a bit about what you're working on today that's exciting for you.
Okay. Well, at the moment, I'm looking at, just from a patent point of view, we need to make derivative molecules. But, the boring way of doing it this week, a long ago, I actually worked in Pfizer just for 1 year. But, what a company like Pfizer would do, would just stick a methyl group on an existing molecule. It doesn't do anything, but it changes the molecule. They get a patent, okay?
Sure.
So on these peptides, yes, you can make those sorts of conservative changes. And in fact, you can boost activity in a certain direction. Well, one of the things I'm looking at the moment is making chimeras. That is taking, say, a human peptide hormone and then mix it with the Ezrin. So you're making basically, it's human still, but you've actually connected human brain and human protein. Now, that may not work, or it may work very well, or we may get a negative signal from it. But if it does work, it's one possibility for coming up with new biological activity, because the way the human system regulates, it isn't like, as I say, a lock and key. It's this huge amorphous sort of interconnection. And you may find if you couple some things to some things, you get some interesting effects. Now, the reason that's relevant to anti-aging effects is because, in fact, some hormones are definitely connected to this aging clock. So you've got the, in the growth hormone systems will stimulate certain pathways, but in fact, these pathways will actually speed up the rate of aging. And you sometimes find inhibition is what slows it down again. So you have to, you can play around. Anyway, I'm just saying these are sort of innovative ideas, but, so we'll do the conservative way, and we'll also do, the possibilities as well, and see if something comes of it.
Interesting. Robert Heffernan had an interesting comment that I would like for you to maybe comment on. He goes, consented harmonized data will be a powerful tool in the near future. And I think there must be a website or a group of individuals working called Secures.ai. What are your thoughts on that?
Well, I think, that first, to have, patients, well, it depends there's a confidentiality question here, but it's very interesting to see if people will publish and say, what, I took this drug, this is the things that happened to me.
Yeah.
Now, and if 1 million people do that, you will actually find a lot of patient-to-patient variation, but you may actually learn some very interesting things about, unexpected sort of retooling of that particular therapy for something completely different. And that's effectively what I've been describing. You went out to treat something and you actually fix something else.
Yeah.
And anyway, it's still probably got to do a huge amount of work to work out why that happened and is it going to be reliable and effective and safe. But yeah, cool idea.
Yeah. It will be interesting to see. And what's fun to me about these conversations is that the future is still being, determined today, right? We have research and data and clinical trials and brilliant ideas like yours that are coming to market to challenge the thinking that we have today. And that's what this really whole platform and podcast is about, is how can we challenge the thinking that we have today, right? I mean, there's a reason that we're no longer bloodletting and doing frontal lobotomies today.
Sure,
Yet
absolutely.
at one point in history, in medicine, that was the thing to do because we thought we had the most conviction of that. And so, once again, you and I could talk all day about this, and we've had some very entertaining conversations over dinner and lunches and some lovely places in London together. So I'm sure we can go on and on about that.
Sure.
Rupert, where can people find you? How can they connect with you? How can they reach out to you? And maybe they want to follow up with having a discussion about what you discussed today. Maybe they are an investor and they're realizing that you're currently raising money for your company and for your clinical trials. Like, where can people find you so they can locate you and connect?
Okay, well, we have a website for the company, which is called Newall R&D. And maybe if you can spread that link around
happy
your
to.
audience. I'm also on LinkedIn, so just look for Rupert Holms. Don't confuse me with the old singer who did, I Love Pina Colada, that guy. We have the same name, but I'm Holms, there's no E, okay? So if you look on Google, actually just Google my name, you will find me. You'll find my publications, and quite often in the publications, if you Google Rupert Holms and Ezrin peptides, you'll definitely find me. I've got about 5 pages on Google.
Brilliant. Awesome. Yeah. Thank you for that. It should be quite easy to reach out to you. And as I have stated before too, like, I will make sure to tag you in this. If there's people who want to follow up, they should be able to find you, and whether they're on LinkedIn, YouTube, or any other social media platform, they should be able to make it happen. So
Cool.
Rupert, thank you for joining me today. Absolutely a pleasure to have you on here. I have so much respect for you. I'm grateful that you came on to share your knowledge today. So, ladies and gentlemen, that's all for today's episode with Dr. Rupert Holms. I hope you found it as enlightening as I have. Rupert, thank you again for joining us.
Thank you,
Our
Eric.
listeners, make sure to remember to tune in for the next episode about the Live More Life podcast. Please go ahead and subscribe to our newsletter, nobodystudios.com/newsletter. And if you have any follow-up questions, please feel free to reach out to Rupert. Rupert, thank you again for joining us, and I look forward to future conversations with you, sir.
Eric, fantastic.
Yeah,
Okay.
lovely. Okay, bye, everybody.
Bye.
We'll see you later, okay?
Bye.